Good morning, ladies and gents. Thank you for the introduction. My name is Andrew, and I form part of the Sorau team here at this Casper workshop. And today I'm going to be talking about a narrowband mode, which is currently under development for the MeerKAT telescope. And I just want to thank Francois. He did me a great favor in producing or showing a bit of an overview of the telescope. So I'm not going to focus too much on that, but rather more details on the actual narrowband design itself. So first of all, we're just going to take a quick cursory glance at MeerKAT, but diving one level deeper towards the DSP side of things. And we'll have a look at wideband versus narrowband, purely because we are currently been using a wideband mode. We'll then look at under the hood of narrowband, some results, current status, and then narrowband going forward, and I'll wrap up. Just keeping to the theme of this workshop, I'm going to try and keep things relatively simple, go with more of a teaching approach, and highlight areas of interest where applicable. So first of all, what is MeerKAT? It's not just a furry friend found in the Karoo region of South Africa, but it's a powerful instrument too. And as Francois showed you with a whole bunch of pictures of dishes in that, it's 64 dishes currently, offset Gregorian type. At the back end consists of 288 scarab boards. Many of you should now recognize the particular piece of hardware. We are working in L-band at the moment, although there are other bands of interest being developed. And in this particular case, we're dealing with dual polarization at the same time. So, if we take a top-level overview of the processing chain, we start off. Let's see if I've got the thing right here. We've got our digitizer, which is at the feed. We then packetize and dump data across an Ethernet network into a switch, which then we hang our scarab boards, and they can either be configured as a X engine or an F engine. An F engine being a channelizer, and the X engine, which is doing our correlation. I'm not going to focus too much on, or I'm not going to focus at all on the X engine, but rather we're going to look at the F engine side of things, and particularly the differences between our wideband and our narrowband, and why we wanted to do this. First of all, when it comes to wideband, we've been dealing with a bandwidth of about 856 megahertz. Now, the general adage is bigger is always better, and it's not always the case. In some cases, you actually want to deal with a thinner range of frequencies, and that's exactly what we're going to be doing. In narrowband's case, we're dealing with a thinner slice, 1/8 of the band, in actual fact, being 107 megahertz. And if we were to kind of contrast the two, when it comes to digitizing, we digitize at the feed. Our data processing in our F engine, we slice out this 856 megahertz bandwidth sitting in L band. And by comparison to our narrowband mode, we're dealing with exactly the same 856 megahertz, except we're just taking one thin slice. Now, this particular image is a static image, just indicating that, or in this case, I've shown that we're slicing out of the center of the band, but the reality is it can shift. And that shift is within about 100 hertz, but we can shift it anywhere across that band at any point in time and work exclusively on that slice of the band. So, just doing a quick contrast, I said we're dealing with L-band in both cases. They both are dual polarization. 856 megahertz in total bandwidth, except we're channelizing 107 megahertz in narrowband. And now here comes the next difference. In the wideband case, we have got three options that we can work on. We can either work with 1K, 4K, or 32K decomposition, whereas in narrowband, we're currently focusing just on the 32,000 channel decomposition. Naturally, 32,000 channels on a smaller slice of the band is going to give you a far finer frequency resolution. And just if we look at some of the use cases, in our wideband case, we use it for things like pulsar timing, imaging, and survey. And in the narrowband case, it's spectral line or imaging work. Right. If we look at just the F engine side of things, I showed you a diagram earlier on where we have data coming in from our digitizer. This gets ingested by our F engine. And first of all, goes through a buffer and a reorder stage. The reason for this is we are not guaranteed that the packets are going to arrive in order, and we need to work with the data in the correct order of which it was captured. So we have to do some reordering. It then goes through a course delay stage, and the course delay forms part of our delay tracking. Earlier on in the week, we had talks about interferometry, where it was shown 2 dishes, and you've got delays, geometric delays that are going to be between them, so you need to compensate for that. We then continue the processing chain into our polyphase filter bank. Again, we had a talk earlier on in the week about it, so I'm not going to focus too much on the underlying processing of that, but we'll just look at the differences. And then it goes into our fine delay stage, which is, again, a adjustment for our delay tracking. It's just working on a finer scale, in other words, not integer multiples of our clock sample rate, which we're needing to adjust per F engine. And then finally, we quantize and packetize and send that data back out into the network, and anything that's interested, in our particular case for the correlator, our X engine will then take in that data. If we look at the narrowband, it's essentially identical with the exception of the 3 stages, one of which is new, which is a DDC, a digital down converter, and then our polyphase filter bank and our fine delay. And the reason I've highlighted those is this is where key changes come in. We've tried to keep the logic exactly the same where we can, so we can reuse it. It's known good, we can trust it, but there are some changes that are needed. So we're going to look at these particular blocks of interest. Right, starting with our DDC. Why do we need it? Why do we want it? Well, as I said, we're dealing with a narrow chunk of band, so we need to naturally translate this down to baseband so we can work with it. Now, we do this by means of digital mixing, which is nothing more than a multiplication followed by some low-pass filtering and downsampling. Now, in this particular case, I've highlighted a particular band of interest. We multiply by a tone or a mixing frequency, which we generate, and I'll detail that shortly, which translates our entire band down, which we can now low-pass filter in order to get rid of spectral components we're no longer interested in, which then gives us the benefit of being able to downsample. We don't need to work with as much data as it is now redundant. But I'm glossing over one very key point here. How do we do this mixing? Where does this tone come from? Well, in our particular case, we have to generate it, and we generate it on the board. So, in this particular case, we're doing complex mixing, so we have to generate a complex signal, and it's nothing more than a numeric lookup of sine and cosine values, which we use in the naive case. You can just apply a counter to your input lookup and read off the particular values for your previously known sine and cosine table that you've got. What we're actually doing in the Meerkat case, we need all of our F engines to work in lockstep. Well, we need to work on the same timestamps, so we use the lower 28 bits of our timestamp coming in. Jason did talk about timestamps in his talk briefly. That is part of our lookup, so we know that we're looking up exactly the same values for each board at the respective point in time. That is then put into our mixer, and we mix with our input data. So, how do we actually do this in practice? I haven't shown the logic for the actual sine and cosine lookup. You just have to take my word for it that it is part of one of our input ports there, but it's nothing more than a Kasparized multiply block coming in where our 2 inputs is our data, which has come from our course delay, and our lookup values from our DDS, or our direct digital synthesizer. We then pass that through a low-pass filter, and we can then downsample. The key point to note at this particular point in time is that we're dealing with multiple samples in parallel. We're still up to and inclusive of the mixer dealing in the wideband case. We have got 8 samples coming in per FPGA clock, so we've got to deal with the 8 samples concurrently. So this is all wideband, wide concurrency that's taking place. The output of our DDC is very different. It is now effectively 1 sample as opposed to 8, and we're no longer working at the exact clock rate. Well, we're working at a still constant FPGA clock rate, clock tick, but except the sample rate has dropped. We're getting, we've got no gaps in our valid data because we are decimating, in this particular case, by 16. If we look at our polyphase filter, we saw a very similar image earlier on in the week, and it's just to highlight the benefits of a polyphase filter as opposed to not using it at all. If we would, the blue trace is indicating if we would just apply an FFT without any form of polyphase windowing or polyphase filter, and then the benefits of using a 4 or an 8 tap, our roll-off sharpens, and adjacent channel suppression improves, which is exactly what we want. There is no free lunch, though. This all costs resources in the FPGA, so you can't just arbitrarily choose some high number. Naturally, the higher the number you get, the better it is, but it's a trade-off at the end of the day. But what this consists of under the hood is a finite impulse response filter, our 32K FFT, and then we have to do, again, some buffer and reordering and some repacking, which I'll explain now. So again, how do we implement this? Using Caspar and Xilinx logic, we've got our FIR filter, again, something that we can apply from our wideband, except we just change the parameters to indicate that we're dealing with less concurrent samples. And then we use, in this particular case, a Xilinx FFT to perform our 32K decomposition. The catch with this, though, is the FFT is putting out our channelized data linearly from channel 0 up to 32767. The problem with that is that it's represented from effective sample area from 0 to fs, rather than from minus fs over 2, where fs is our sample rate, to positive fs over 2. So we need to repack that. And how do we do that? We essentially are buffering up part of the first and second part of our spectrum, and we swap them around. So we want to be able to allow the higher part, in other words, from the edge of our band, which would be from fs over 2 through to fs, and then the subsequent part thereafter. And you'll see in reality what it looks like when I show some results. There is, however, also one further problem going forward. To reuse existing logic, what we're wanting to do is still work with the wideband case, where we're dealing with multiple samples in parallel. So we need to repack this, which is effectively nothing more than a serial to parallel converter. So we buffer this data up. We only issue out our data valids every fourth sample in this particular case, so we can pass out 4 complex samples per data valid, which is going to be synchronous to our clock. This allows us to be able to leverage existing logic further down the line, namely our fine delay and quantized logic. Now, when it comes to our fine delay, if you remember, I referred to earlier on to our course delay, where we said it was exactly the same in both the narrowband and the wideband case. We're dealing with an 856 megahertz bandwidth, which is all fine and well, but in narrowband case, we're only looking at a particular slice of it. So that naturally means when we're applying a fine delay for our phase compensation, we only want to work on that particular slice. So we've made some changes to the existing logic, and what we do is we have a look at the frequency of request, for example, what we're wanting to mix at, so we know where we are in the band, and we only work over that particular chunk of the band when we're applying our fine delay. So these 2 lines that are in red, they shift. So depending on what our band of interest is within this 856 megahertz bandwidth will depend where we are on our phase slope. So that changes. This is just a static representation of that. What does it look like in practice? This is an actual result grabbed off our correlator, which is busy running. We've got a relatively flat pass band. What we're doing in this case is we're ingesting noise, and I put in 2 tones, and I intentionally chose them almost back to back with a 1-channel spacing, so we can see that we are able to actually resolve them in our narrowband case. So in this particular case, we can see where we roll off to near the ends of the band, and if we were to zoom in on this, what looks like a singular tone from the top diagram, we can actually see we get our two tones popping up. The one happens to be sitting at band center, and the other one I've offset by 2 channels. And if you work it out, you'll see that it works out at just over 3.2 kilohertz per channel is what we're getting. Where are we at the moment? Well, we have a working system. We are ironing out a few bugs. Some noise here and there that we need to clear up, but it is operational, and it is currently undergoing some verification testing and system integration to get it to work with the rest of the system as well is underway. Of course, there's no free lunch, and what does this look like currently in terms of resources on our SCARA boards? Essentially, it's very similar to our wideband case, with the exception DRAM. We're sitting at just over 90% at the moment for our dual polarization 32K mode. So it's not always place and route time enclosure friendly. However, the new TwoFlow or the newer versions of Avado do a better job than the older ones. So it's not as painful as what it was a few months ago. Just looking ahead in the future, there are a few other narrowband modes that have been planned. This is just one of them that we're working on at the moment. We are only looking at one slice of the band at the moment at 107 megahertz wide. However, there is planned to be up to 5 of various widths, and our decomposition goes down to 4K as well, not only 32K. And it's also to include UHF band as well, where we're only looking at L band currently. Just to wrap it up, I've laid out some of the narrowband specs that we're only looking at 107 megahertz at the moment. And in order to realize this, we've had to implement some additional logic, that being our mixing stage and our DDS, as well as our digital line conversion stages. We've had to bring in some reordering and some repacking, as well as make adjustments to our fine delay logic. But of course, all of this never comes free, and there's always ins and outs that you have to play around with, and resources are something that we're always looking at trying to improve. And then, of course, going forward, we have got some other future narrowband modes on the cards, but that is something that'll be cleared up over time as to exactly what the specs are for those. Thank you very much.
I appear to be building exactly the same thing in my Curtis Wright board this year. How many channels, is this the whole FPGA that's filled up with this, or is it just part of the thing? Do you reconfigure, or is this in addition to the wideband?
No, this is a completely separate bit file that you're going to drop on there. It's those resources that I showed you, that's the entire chip. We don't run them concurrently. It's either a narrowband mode or a wideband mode that we run. That's a good question. I think
point out that there's 3 HMC controllers in there and a 40 gig core, which use more than half of the chip.
Yeah.
Yeah, I was wondering what fraction of the chip was available.
Yeah.
The DSP part is actually a small fraction of the consumption.
Any other questions?
How long does the build take?
On average, well, I suppose it depends what else we're doing on the PEC, but work on about 5 to 6 hours. So if we're lucky, we can get 2 through in a day, if we're making changes. But realistically, it's a good 5 to 6 hours.
Our longest build takes 14.
Yeah.
Are the Meerkat designs in a public repository?
Yes, MCAT FPGA is where it all lives.
Is that public source?
Yeah. If you
Because I've somehow infiltrated the SK Git
Oh.
organization, so I can see them anyway. It's kind of interesting if this stuff is just...
No, it should be public. If my memory serves me correct, we do have a FNG wide and FNG narrowband. If you do a git pull, you'll see those. So they are separate. It's not just a parameterized thing. It's a separate SLX completely.
All right. Thank you,
Good.
Mr.
Yeah.